Hi, in this video I'll be talking through parts of this handout on polynomials, zeros, and roots. I'm not going to go over all of it. When I presented this in class, I only went over some parts of it. So what we're mainly going to focus on is, generally speaking, what polynomial graphs look like and how to find the zeros for polynomial functions. So here we have what's called the standard form of a polynomial function. And so it's just powers of x, whole number powers of x, with coefficients in front all added together. So here's a very concrete example. Usually we write this in standard form with the powers going down. X to the third, then x squared, then x, then a constant at the end. Now, let me just tell you some general things about polynomials, some of which we did through Desmos exploration. So just worth knowing, kind of the building blocks of polynomials are what are called power functions. And if I take really dull things like y equals x squared, y equals x to the fourth, y equals x to the sixth, y equals x to the eighth, etc. Basically all of these are even positive powers. Those graphs are all going to be reminiscent of x squared. They're not literally the same shape, but they're very similar, right? So they're like x squared in their general appearance. I'm intentionally not putting coordinates here because the details vary, the overall shape doesn't. While if I do it with odd powers, and I'll start with 3 just because that's a little more interesting, etc. If I have x to an odd power, they have this appearance like so. So with even powers, there's this symmetry where left and right are both pointing in the same direction. With odd powers, it's up on one side and down on the other. Now, it's a little hard to tell these apart. Usually with a polynomial, we have multiple terms. And just as a handy rule of thumb, it's worth knowing that the number of x-intercepts for a polynomial graph is always less than or equal to the degree being the biggest power of x that we see. So with that in mind, we can look at graphs and kind of guess how complicated the polynomial function is. So here, for example, we see 1, 2, 3, 4 x-intercepts. So the degree would be at least 4. Might as well just guess 4. So this is probably degree 4. And we notice that it's doing what x to the fourth would do. If it's doing what x to the fourth would do, that means it's starting with a positive number. So we can also file away that the leading coefficient is positive. Let's look at this one. This one has 1, 2, 3 x-intercepts, so probably degree 3. We can see that what this is doing, there's some wiggle in the middle, but kind of, if we zoom out and squint, it resembles what x to the third is doing in the same direction. So again, would have a positive leading coefficient. Here, well, this is a line. Lines are polynomials of degree 1. Right? There's an x, but it's not raised to a power. And here, right, we could actually calculate this. The slope is negative 2. The y-intercept is 2. So that leading coefficient obviously is negative. And here we see 2x intercepts. This looks like a parabola, which would be degree 2 because of the x squared. And it's pointing down, so it has a negative coefficient at the start. Just a bit of vocabulary that you don't have to necessarily know. Degree 2 is also called quadratic. Degree 3 is sometimes called cubic. Degree 4 is called quartic. And degree 1 is linear, right? Degree 1 polynomials are just lines, which we're familiar with. So even when we have more exotic things, we can get a rough sense of what these look like by transformations. So, for example, here in green is y equals x. We could look at this and think of it in terms of transformations. The 5 that we're multiplying by makes it 5 times as tall. And the -3 shifts it down by 3 units. So our graph would be something that's steeper but shifted down, something like so. The y-intercept is lower, but this graph is much steeper. So here would be our graph of f of x, something like so. For all of these, if you know what the basic power function inside looks like, you can graph these by transformations. So for this one, we want to compare it to normal x squared, which I'll draw over here. Normal x squared looks something like so. It's going to be 5 times as tall, shifted 4 units to the left, shifted 3 units down. So the vertex would be at -4, -3, and it would be 5 times as steep as our normal parabola. And that's what we're doing with all of these. It's 5 times as steep, we've shifted it 4 to the left, and we've shifted it 3 down. So this one would go through -4, -3, but would look like a steep version of the x cubed graph. This one would go through -4, -3, and would look like a steep version of the x to the 4th graph, which pretty much looks like x squared. Without going into extreme detail, it's sometimes hard to tell those apart. Okay, we're going to skip some of this stuff. Okay, end behavior. We've sort of hinted at this, and I've mentioned it in other things. But let's get this into one summary here. If we know the leading coefficient of a polynomial, and we know the degree of that polynomial, we know what the end behavior will look like. End behavior is what the graph is doing on the extremes. So for example, if I have a positive leading coefficient and an even degree, that means the end behavior ultimately is like x squared. So if we imagine the graph of x squared, on the extreme right, it's at the top. On the extreme left, it's at the top. Now in between, maybe it has some wiggle. That's certainly possible. But this end behavior would be completely predicted just by knowing we have an even degree and a positive leading coefficient. Another possibility of the graph, perhaps it looks something like so. Different graph, but same end behavior. If I go far enough to the left, it's pointing up at the top. If I go far enough to the right, it's pointing up at the top. If the leading coefficient is negative, it would look like one of these graphs, but upside down. Maybe it would look something like so. This would be a possibility for a polynomial graph with even degree but negative coefficient in the front. Or maybe it looks something like so. This would be a possibility, has some wiggle to it, but eventually on the left and on the right, it's at the bottom pointing down. So all of these have end behavior that would be like x squared or like negative x squared. For odd degrees, it would be like x cubed or negative x cubed. The graph of plain old boring x cubed looks like this. Right, this is y equals x to the third. The coefficient here is an implied coefficient of 1, which is positive, odd degree. We might have more exotic examples, but they would have the same end behavior. Maybe we have a graph that looks like this. There's more wiggle to it, but the same end behavior. Negative on the left or pointed down, positive on the right, pointed up. If the leading coefficient is negative, it's upside down. So it might look something like so. It might look something like so. There are lots of possibilities for the details of the graph, but just by looking at two pieces of information, the degree and the coefficient we start with, whether it's positive or negative, we can more or less predict what this graph looks like on the sides. So what we can do to draw rough graphs of something is to think about the degree and to think about the zeros. Zero or root is basically a fancy word for x-intercept. And we can find the x-intercept by setting things equal to 0. We set the function equal to 0. If it's factored, we're in good shape. So we find this by setting equal to 0. So let's take a look at this first one. Let's just note, if I multiplied these together by foiling, it would start with x squared, and if I multiply by x, it would start with x to the third. I don't actually have to do the algebra to realize that the first thing here is x times x times x. It would start with x to the third. So that's odd degree, so degree 3, and a positive coefficient. Now, if I were to set this equal to 0, it's already factored, which is great. By the zero product rule, if a bunch of things multiplied together are equal to 0, then at least one of the individual factors has to be 0. And this is how we find what are called the zeros of the polynomial, or the x-intercepts of the graph. This value would be equal to 0. Y would be 0 when x is 0, or when x is 7, or when x is negative 3. So we found our x-intercepts by factoring. We know the end behavior will be like x to the third, so far enough left, it's down, far enough right, and make sure you go left and right of these points. Far enough to the right, it's up. And then we just play connect the dots as best as we can. Like so. When in doubt, it passes through those x-intercepts. I'll explain when it doesn't. Let's look over here. If we multiplied this out, we get a 3x here. We would get an x to the third here. So this would start with 3x times x to the third, which is 3x to the fourth. So degree 4 and a positive coefficient. Now if we set this equal to 0, either the first factor is equal to 0 or the second factor is equal to 0. Now if something is being raised to a power like this, that number is called the multiplicity. And the multiplicity tells us what the graph is behaving like near that x-intercept. So here's what you want to know. If you see an even multiplicity, we have what's called a touching x-intercept. If we have an odd multiplicity, it's crossing. So what's going on in this case? If we solve this, we would get x equals negative 4/3. If we solve this, well, if something cubed is 0, that something was 0, and x equals 2. So I have an x-intercept at negative 4/3, an x-intercept at 2. My end behavior is like 3x to the 4th, which is positive on both sides. And so my graph would be like so. Crosses here. Now, degree 3, it crosses in sort of a wiggly way. That's not an essential detail, but if you were to graph this on Desmos or something, you'd notice around here the graph is kind of flat as it crosses. That's a minor detail. Let's look at some more. So for a lot of these, the trick is to factor it correctly. So let's go. If we factor, if we factor this one, we notice everything is even. So we have 2 times x squared plus 7x plus 6, which is 2 times x plus 1 times x plus 6. So the degree is 2. End behavior will be like 2x squared. If I set these equal to 0, my x-intercepts, also known as roots or zeros, all of these kind of mean the same thing. If the first one is 0, x is negative 1. If the second one is 0, x is negative 6. So I have an x-intercept at negative 1, an x-intercept at negative 6. My end behavior is like 2x squared, so positive here, and the graph looks something like so. You can check that using a computer, and we did a decent job. For some of these, you really have to play around with the window. So it wouldn't look exactly like this shape if you just put it into Desmos, but if you played around with the window, you could make it look like that. Let's look at this one. We'll notice that the terms are not in the usual order. That's a bit of a trick, so we'll fix that. And we'll notice that this is x minus 5 times x minus 5, which is x minus 5 squared. So the x-intercept is 5. That's the root, or the 0. But it has a multiplicity of 2. That means that when we see the x-intercept, it's going to be touching. Even multiplicities correspond to x-intercepts where the graph touches the x-axis without crossing through. So here we have a touching x-intercept at 5. Our end behavior is like x squared, which would be positive over here and positive over here. So the graph looks like so. When I get to this x-intercept, I'm not going to cross through. I'm just going to bounce off the x-axis like so. Let's look at this one. Again, kind of in a weird order here. Let's fix that. So r of x is negative 12x cubed plus 60x squared minus 75x. I will notice that everything here is divisible by 3x. I'll actually pull out a negative 3x. That'll make the factoring easier. So if I pull out a negative 3x, I get 4x squared minus 20x plus 25. This factors as 2x minus 5 times 2x minus 5. So here is our factorization. We'll notice again an even power. So we have multiplicity of 2. We have a touching x-intercept. So by the factorization, either negative 3x is equal to 0, which means x is 0, or 2x minus 5 squared is equal to 0, which means 2x minus 5 is equal to 0, which means 2x equals 5, which means x equals 5 halves. And this is a touching x-intercept. So when we graph this, there's an x-intercept at 0. There's an x-intercept at 5 halves, which is 2.5. Our end behavior will be like negative 12x to the third. So this is the end behavior when we start with a negative and have an odd degree. So our graph will look something like so. We just play connect the dots. This one is crossing, sort of default is crossing. And we come up here, this one is touching. It's just going to bounce off the x-axis and turn around. Our graph will look something like that thing in blue. We've got a couple more. For this one, right away I'll factor out that negative so the factorization is easier to see. This factors as x squared minus 1 times x squared minus 1, which is x plus 1 times x minus 1 times x plus 1 times x minus 1, which is x plus 1 squared times x minus 1 squared. We're seeing these even multiplicities again. So my x-intercepts are at negative 1 and 1, and both of them are touching because we have even multiplicities. So here's negative 1, here's positive 1. My leading coefficient is negative, and we have an even power. So my end behavior is going to be like this, like an upside down parabola. And I have these two touching x-intercepts. So the graph looks something like so. Bounces off the x-axis in two places. Okay, we've got 3 more of these. The factorizations can get a little bit tricky. This one factors as x squared minus 4. Oops, sorry, x squared minus 4 times x squared plus 1. Right? The trick is to pretend like this is x squared and this is x and just use the pattern. And then this factors as x plus 2 times x minus 2. This thing here doesn't factor, this last one. Oops. This is never equal to 0. So our only x-intercepts come from these two. So although this is degree 4 can have as many as 4 x-intercepts. This one only has 2. So the graph, as far as we know, probably looks something like so. End behavior is like x to the 4th, and it has crossing x-intercepts at 2 and negative 2. This one we can factor by grouping. For 4 terms, you can try that. We'll notice x squared can be factored out of these first 2. Negative 5 can be factored out of those 2. So we have x squared minus 5 times x plus 5. If we set this equal to 0, we would have x squared minus 5 equals 0, so x squared equals 5. X is plus or minus square root of 5. If we set this equal to 0, we get x is negative 5. So we have an x-intercept at negative 5. We have an x-intercept at the square root of 5, which is about 2.2. Another one at negative square root of 5, about negative 2.2. Our end behavior is like x to the 3rd, so positive here, negative here. And these would all be crossing x-intercepts. So it would look like so. And we have one more. Let's fix the order. This looks like another candidate for factoring by grouping. Here we can factor out 9x squared, and we're left with x minus 1. Here we can factor out a negative 49, and we have x minus 1. So 9x squared minus 49 times x minus 1. This first part here is a difference of perfect squares. So that factors as 3x plus 7 times 3x minus 7 times x minus 1. To find the x-intercepts, I set all these equal to 0. This one would be x equals negative 7/3. This one would be x equals positive 7/3. This one is x equals 1. All have a multiplicity of 1, so they're crossing. End behavior is like 9x cubed. So what do we have here? x-intercept at 1, x-intercept at 7/3, which is about 2.3, x-intercept at negative 7/3. End behavior is positive over here, negative over here, so something like so. There we go. So I went through this quickly. Don't panic if some of these factorizations were not obvious to you, but the key things you want to know, just to summarize, you want to know how to find the end behavior. You find the end behavior just by looking at the first term, assuming it's in standard form, and we have this table up here. It tells you everything you need to know. We also want to know how to find x-intercepts by factoring. And finally, what we want to know is how to identify the touching x-intercepts, which are less common, but we'll still see them, by looking for even multiplicities. If we see a factorization where something is squared, then we know we're going to have one of these x-intercepts like so, where the graph bounces off the x-axis instead of crossing through it. So these are really the key things. Individual problems might seem tricky if the factorization is hard, but as long as you're comfortable with these, I don't think you have to stress too much. Okay, that is the end of